Good morning, good afternoon, and good night, and good evening, like everybody, depending on where you are. So I'm in Europe, so for me it's the afternoon. And today we have the pleasure to have Dr. Daniel John Preston to give us the talk for the TTC this week. And to briefly introduce Professor Preston, she's a very good friend of mine from our years during our PhD. And right now, Dr. Preston directs the Preston Innovation Laboratory at Rice University, conducting research at the intersection of energy, materials, fluids, and robotics. He's a recipient of the NSF CAREER Award, the ASME Old Guard Early Career Award, and the Energy Polymer Group Certificate of Excellence. And recently, he was also a recipient of the Ig Nobel Award for his work in soft robotics. But today, he will tell us more about his work related to the thermal community. And the title of his talk is Mitigating Chemical and Thermal Failures of Engineered Wettability Surfaces. And with that, I'll give the mic to Dan and I look forward to your talk, Dan.
Thanks a lot, Jungmao. Yeah, it was funny. I was up in Boston maybe 3 weeks ago, and I saw Matt, who's there. He was gracious enough to give me a tour of the Bucci Red Lab, and so I'm really grateful for that. And then Jungmao, I saw more like 2 weeks ago. I have this picture. So thanks, Jungmao, for the great introduction. As he mentioned, we like to work together, and I've had a nice history of collaborating, but we're also friends outside of lab. And I had the chance to visit Jungmao in Switzerland, and here we are in front of the Matterhorn. And so this was a really nice trip, but actually was spurred by the opportunity to give a talk at EPFL. So not just for pleasure, but also for business. And so here's the evidence of that photo from the talk. And in the talk, as Jungmao mentioned, it was focused a bit more on some of our soft robotics work in the group. And so I have just a couple of slides in case you felt like you didn't want to miss out on what I talked about when I was visiting Jungmao on some of the things that we're doing there before I get into the main focus of today's talk. So we've been looking a lot at soft and fluidic control. Soft robots are typically made of elastomers or other soft materials, and oftentimes they're actuated with pressure, maybe pneumatic or hydraulic pressure. But a lot of the times they're controlled with a circuit board and some solenoid valves. And so typically the controllers are not soft. We cannot make fully soft robots. And we said, how about we try to replace the voltage and current with pressure and fluid flow? This is an idea that's been around actually maybe since the Cold War, looking at fluidic controllers to avoid things like electromagnetic pulses. But now we're building it into fully soft architectures like this pressure-based transistor in the top left, combining them for sequential actuation with just one constant uniform pressure source in the top right, and even doing things like sensing, responding to human users in the bottom left, and more complex operations in the bottom right. In the bottom right here, we travel forward, grab an object, and then we come back to our start location, and this is only using the air from this CO2 canister to govern this motion. So I find this to be a really rich area. We're actually moving now into using this technology in wearable robots. So developing this in 2D textile-based architectures, again, using this fluidic logic, computation, and control. And so starting from something like an inverter to full, what we would call like integrated circuits fabricated in sheets of textile. And maybe for things like thermoregulation, where in this case, completely without electronics, this user can press a button on their shirt, maybe useful for folks that have limited overhead mobility and can't put on their hood when they're cold. In this case, the hood comes up and we have one bit of fluidic memory on board such that the hood will stay up until the user presses a different button on their garment to put it back down again. And in addition to that, we don't want to have to carry around a CO2 canister. So we've been thinking a lot about energy harvesting in these wearables as well. And that might look like the video on the right here, where we have a user with an insole device. Every time she takes a step, we see a spike in force measured in the shoe. And over time, we have a device in there that pushes pressurized fluid into a bladder around her waist. And that pressure builds up to about a bar over a couple of minutes of time. And then we can use it for things like in the bottom video here, maybe some useful actuation with this supernumerary or third arm. And again, this is all just pressure-based, so we don't have any electronic components in these wearable systems. And that helps us overcome a typical failure point with these wires as they bend over and over again as you wear a garment or put it through the washing machine. We kind of overcome that limitation. And so we were excited about this. We'll be working on this for the next few years, supported by our lab's CAREER Award. And I encourage you all to think about it too. This community, I think, has a lot of really great expertise in the thermal and fluid sides that can really push the field of soft and wearable robots forward. There's another area that I'm not going to talk about today, but that I just wanted to mention because I think this is really cool and I think may be of interest to some of you. So I have just one slide on this area, which is thermally accelerated reactions. And so here we got into this area during the pandemic, the COVID-19 pandemic, with some funding from the National Science Foundation to think about how does the virus lifetime change, or how is it inactivated at different temperatures, maybe at different climates, or even if we can use this understanding to, for example, decontaminate personal protective equipment like masks in our home ovens, and found that there is a strong, in fact, exponential dependence on temperature of this virus inactivation rate. And later, we actually used this to develop what we would call self-decontaminating wearables. And so in this case, the user taps the back of their glove to a wall panel. Within 5 seconds, the front surface heats to over 100 degrees Celsius. We designed it such that the thermal properties prevent the user's skin from getting hot. And in the plot on the far right, we show that we get more than a 99.9% reduction in virus present at the surface. So this would meet the FDA guidelines for decontamination here. And so it doesn't only apply, of course, to viruses and biomaterials. It also applies to soft materials, things like elastomers, and even things like epoxies. All kinds of reactions are governed or accelerated thermally. And so in this case, we're now looking at extending this understanding or this framework to things like processing elastomeric materials for soft robotics applications, where if we use elevated temperatures for manufacturing of soft robots, we can get a much higher throughput. We can generate many more components per time. So showing so far in the lab an increase in productivity of about 1 to 2 orders of magnitude. So these are some of the other areas we've been exploring in our group, things that I'm happy to talk more about maybe offline, and that I hope I can convince some of you are interesting enough areas to also start to step into. I think that there are a lot of cool untackled problems here, again, that folks with our expertise can really do a good job of trying to address. In this case, this might seem like a few different disparate areas, but actually we would say that in our lab, these are all related to our key focus and expertise, which lies at this intersection of energy, materials, and fluids. And so I like to set this context to kind of let you know what we think about, and also take a moment here to acknowledge all of the grad students, our postdoc and undergraduate researchers working in the lab. Certainly without them, we couldn't have done any of this work. And so now I have the chance to circle back around and, as Jungma mentioned, talk more about some of the work on engineered wettability for these thermal applications. And I'm going to look at both chemical and thermal failures of surfaces that we design or tune with engineered wettability. And I'm going to start today's talk by looking at some of the chemical failures that we might typically experience or encounter. So in condensation applications, which I'm sure at least half the group here is quite interested in, we typically try to move from film-wise to drop-wise condensation. In this case, we get nice high droplet mobility. The droplets shed from the surface and keep the thermal resistance low. And this transition is not the only way to improve heat transfer performance. There's other ways to remove fluid from the surface effectively and keep the thermal resistance down. Some of those approaches are summarized in the plot at the right here by Kyle Wilkie. And we see that basically all of these are limited in terms of robustness to some time period. If we use thick polymeric coatings, maybe also finned or extended surfaces, we can push that to higher operating periods, but at the expense of having lower heat transfer enhancement. And folks have been addressing this. So Kyle in the same paper also proposed a porous infused polymer surface. And so in this case, this improves over much longer periods of time, this heat transfer enhancement with dropwise condensation. Other folks like Adam Paxton in the Varanasi lab have looked at this. And if you've talked to Ninad lately, Ninad has most definitely talked to you about his 3-year condensation experiment. He's very excited about this. And fortunately, these results were also just published maybe very recently in Nature Communications. And so a lot of good progress in trying to improve condensation to longer time periods and avoid this degradation of the surface chemistry that transitions us back to film-wise. And in fact, a lot of cool work lately has been focused on getting dropwise condensation almost naturally or spontaneously via contamination. And so I refer back here to a decade ago when a paper came out in Nature Materials on rare earth oxides, suggesting that these might be a good candidate to promote dropwise condensation. And we have some images from their paper here showing condensation on the surfaces of two of these rare earth oxides, nice dropwise mode compared to bare silicon. In their paper, they said that maybe there's an intrinsic hydrophobicity. In follow-up work that I led, we actually proposed that maybe this is indeed due to some contamination of these high-energy surfaces over time instead. Either way, we get some nice dropwise condensation, and there seems to be a consensus in the following literature that there's this contamination effect that results in this nice dropwise mode of condensation. More recently, people are actually using this to get things like jumping droplet condensation, which can help to push the heat transfer enhancement even further than with just gravitationally driven dropwise condensation. And a lot of folks are doing really cool work in this area. In fact, I'm showing here the title of a paper with a group of authors that are all interested in this area, led by Danny Orahon. This is not out yet, but it's in the second round of peer review. And so hopefully you'll have a chance to see a nice summary of all this work using contamination to improve condensation heat transfer among other applications in this paper. And actually just 1 week ago, this past Friday, we had Danny here on campus at Rice University, and he gave a nice talk regarding some of this work. So really happy to have had the chance to have him come by. So with condensation, it seems like we're getting actually an advantage from this contamination on the surfaces, resulting in dropwise mode and improving heat transfer. But for boiling, it's a different story. So boiling, if we're getting contamination on the surface, first of all, it ends up usually reducing our heat transfer performance. And second of all, providing a lot of inconsistency in experimentally reported values. And so we think about the critical heat flux, for example, definitely linked to things like the surface chemistry and the geometry of the surface, things that you want to control very carefully for some of these surfaces with engineered wettability, and things that you want to make sure that you also keep consistent when you're trying to do fundamental studies of CHF on maybe metals, different types of structures. But we find out that, for example, in this paper, looking at just the literature regarding silicon and silicon dioxide, that the reported critical heat flux values, even when these surfaces are nominally flat, are all over the place. They vary by maybe 50% or more. And so there's a lot of disagreement in the literature on what is the critical heat flux value on these surfaces. And so we've conducted some work here to try to understand or explain why that might be. In this case, we took some smooth silicon dioxide surfaces, we plasma cleaned them and exposed them to lab air for different periods of time, and then did pool boiling experiments. Pool boiling experiments versus the air exposure time shown in the legend looks something like this. And if we plot these on the same plot as the percent carbon that's measured on the surface, what we find is that there's sort of this inverse correlation. And so just leaving it sit out in the air, in the lab over time, after a sample has been cleaned, will result in adsorption of carbon on the surface. It will become more hydrophobic, and that will really seriously impact your critical heat flux value. So this is something I think I've tried to make the point here that is very important to consider, even when you're doing fundamental studies, let alone trying to do things like enhance the performance with engineered wettability surfaces. And so people have said, maybe we can try to limit or mitigate this contamination with something like ultra-high vacuum, especially when we're doing some of this surface metrology, or maybe when we're trying to store surfaces to keep them clean over time. And so we limit the pressures to these low values, maybe below 10 to the -8th torr or so. And it's used in a lot of common techniques, including XPS, SEM, and even things like the Large Hadron Collider. This has been used for actually a lot of surface applications where we want to keep surfaces clean. The sort of understanding in many of these industries is that we can use ultra-high vacuum, for example, in semiconductor fabrication, in things like diagnostics, fundamental studies, and also maybe things like anti-reflective coatings to try to keep the surface clean. We can just apply vacuum. And so I put the question mark here because we set out to sort of probe whether this is really true. Can we just use vacuum to maybe keep a surface clean? And an interesting anecdote here, a story that you can look up in the news, is that the standard kilogram has actually gained weight over time Reason for this is because there's a thin layer of adsorbed contaminants on the surface. They probed this and found that some of them are mercury-based. Most of the contaminants are carbon-based. And so there are some hydrocarbons from the air that make their way into this sealed chamber, even under vacuum, and stick to the surface of the standard kilogram and change the value. And this has been reported, actually, if you really jump in and look at the literature in depth, in a few papers over the years. So exposure to ultra-high vacuums actually can lead to, in fact, faster contamination. And there's been some studies that claim that, maybe using the vacuum to prevent the contamination are not appropriate. And so in our work, which came out last year in Langmuir, we tried to look more quantitatively at this temporal evolution of surface contamination under ultra-high vacuum. So a quick overview of the experiments that we conducted to probe this area are shown here on the slide. We wanted to start in some ultra-high vacuum environment with samples that have different levels of contamination. Maybe a clean sample to see if it stays clean. Maybe some samples that are also already contaminated to see what happens to those as well. In this case, we used an XPS chamber for our ultra-high vacuum environment. And then we wanted to know what happens over time, right? So that's what's the question mark here. What do we observe? And so we fabricated some surfaces that were flat and gold. And so we zoom in here and we can look at the surface morphology and find that the roughness is quite small. So we expect these nominally to be flat and nominally to be fully gold-coated surfaces. We pre-treated them. So in this case, we have 3 different types of pre-treatments. First, we just take 0 hours in lab air after cleaning. That's not going to have much contamination, so as deposited here. And then if we let it sit in lab air for different periods of time, we might call these a partial contamination, not fully contaminated with hydrocarbons. And then maybe if we let it sit for much longer, it becomes sort of approaching some sort of a steady value in terms of the contamination. So we take these 3 types of samples, put them in the chamber, just to make sure that our clean sample is in fact fully clean. We do an ion gun sputter inside the chamber, and then we see what happens over time. And what we observed, it's just summarized here schematically, and we'll go into more detail in a moment, is that the clean sample adsorbed contaminants even inside the ultra-high vacuum environment. And the samples that were contaminated actually desorbed contaminants. And so you might have a sample that you just pick up from the bench in lab, put it in the XPS, try to quantify it. You'll find that, in fact, the composition of that surface is changing over time as a result of sitting in the ultra-high vacuum environment, and you may get inconsistent results there too. We looked at this time varying surface composition. So this is the in situ cleaned sample that was sputtered with the ion gun in the XPS chamber. And over time, 4, 8, and 18 hours, we see an increase in this carbon peak measured with the XPS instrument. And so that's shown here in the plot on the right. We get an increase in the carbon atomic percentage that we can calculate from the XPS as a function of time in the chamber. Conversely, we said we had these other 2 samples, one of which is partially contaminated, and the other is fully or stably contaminated. And I mentioned that those actually experience desorption of contaminants in this ultra-high vacuum environment. And so this effect is almost omnipresent unless you happen to start at this equilibrium level by luck. And this is a result that is measured converse to the gold concentration on the surface. As we might expect, we're covering up gold sites with carbon during contamination, or vice versa. If we're desorbing contaminants from the surface, we're seeing more gold. And all these approach some sort of an equilibrium, which we kind of see from the data here. So we tried to conduct some theoretical analysis to better understand this. We wanted to develop a model that could explain the results that we're seeing. And we did this with some hydrocarbon adsorption-desorption theory on the surface. And in a gaseous atmosphere, typically you might model some adsorption based on the molecules hitting the surface, some sticking coefficient, and some desorption maybe based on this spontaneous popping off of particles or molecules from the surface. In the vacuum environment, we could not use these exact same quantities, but we could still say that it's a competition between some adsorption, which might be related to the chamber conditions. For example, just looking at the stage itself, there's a lot of carbon present since the stage is coming in and out of the chamber many times during use. And then also some desorption that's related to the surface concentration of hydrocarbons. And so again, showing the same data here, we started by just taking that model, fitting it to our sample that was contaminated over time after initially being cleaned in the chamber. And from there, we were able to calculate these coefficients A and B for the model and use them also to try to explain the partially and stably contaminated surface evolution for contamination over time as well. Seemed like a pretty good explanation. We did not quite get down to the same low level of equilibrium with the stably contaminated sample. And so we also fit a different value of B, which we called B prime, to the data points themselves up here. What we probably expect happening is that we have a transition from some initial hydrocarbons on the surface that have been stuck on there from the air environment, and then later some hydrocarbons that have been transferred onto the surface from some inside the XPS chamber environment. And so these might be different species. And it could be the case that in a conservative situation, we're actually left with mostly the contaminants that are initially from outside of the chamber. And so we sort of bounded this prediction, but we found that all of the data points lie within the shaded region. So we were pretty excited by the ability to use this model to describe the experimental results. But we wanted to make sure that it was not just our system. And so we worked with a different system. This system was at MIT. It was an XPS chamber in which we could measure the carbon percentage over time. And we had a couple of samples. So in this light, almost salmon color, we had an in situ clean sample in the MIT XPS chamber. And this mirrored almost exactly our results obtained at Rice. And we also looked at an initially contaminated sample that had been sitting in the lab air for days, put that inside of the XPS chamber at MIT in these sort of red colored X markers, and found again a nice agreement with the results that we had already obtained at Rice. And so in this case, the results here were obtained by Young-Sup Song, who's going to be starting his professorship at the University of Florida, I believe, pretty soon. Question might come up, well, what if the vacuum just wasn't a high enough level? What if we go to even higher vacuum or lower pressure, right? We were already at a value of pressure such that the mean free path was bigger than the size of the chamber. And so our guess is that just increasing the vacuum level will still have only ballistic transport and probably still have contamination of the surfaces in the same way that maybe just regular 10 to the minus 8th torr in the XPS chamber would have given us anyway. So basically, we looked at this ultra-high vacuum storage. We found that we sort of, in this case, have this time-varying behavior. They both approach an equilibrium value inside the chamber that's likely related to the chamber walls themselves having some contaminants. We use the absorption-desorption competition model to describe the behavior over time, and said that maybe the cleanliness of your chamber is quite important, right? So maybe in this case, the XPS chambers are heavily used equipment. We have lots of samples going in and out. And maybe the walls of the chambers themselves are quite dirty. So this is something that you should really consider when you're trying to run experiments and carefully calculate surface characteristics, because even over the time scale of hours, this can alter your results. All right, so I'm going to move into stage 2 of the talk, coming back to this inconsistency in the CHF values, right? So this is something, again, that we said people are testing samples in their boiling rigs, and they're getting all kinds of different values. We would like to keep this consistent. Maybe we would like to keep the surfaces nominally hydrophilic. Maybe we want to keep our contact angles close to 0 to improve the performance and keep the results consistent. How do we do that? So we said ultra high vacuum is maybe not the approach, right? That's what we just talked about. And this is a problem that's really pervasive. You know, there's these hydrocarbons that can stick on your surfaces, not just in the ultra high vacuum environment, but almost anywhere you store your samples. And it comes from things like solvent vapors in the lab, pump oils, and maybe sticks on the surface and over time evolves and eventually covers the surface, right? In our case, we said, well, if it's going to cover this area of the surface, maybe what we can do is build a texture enhanced storage vessel such that the walls of this container in which you store your sample actually try to pull away most of the contaminants such that they don't stick to the sample remains clean. And so we did this by enhancing the surface area of the container walls and also making sure that those walls with the enhanced area were ultra clean at the point at which you store the sample. And then basically the container is sacrificial. It pulls all the contaminants such that the sample remains clean. And we compared this to a couple of other methods, vacuum and different types of wafer holders or Petri dishes, as well as storage in air. These methods were not effective. We still had an increase in the contact angle over time as a proxy for the carbon contamination. But with our approach, over in this case 40 hours, we had no observable increase in the contact angle over time. So this is just like sort of the summary. We'll get into some details. Here's the container. We structured the inner wall by either sanding or hot water treatment or both. And then we used plasma treatment. So it would look like either a non-treated flat surface, a surface that we used hot water treatment on, or one that we sanded and then used hot water treatment on. In aluminum, the hot water treatment forms these nice leaf-like nanostructures. And then in all three of these cases, we used the plasma cleaning to make sure that the inner wall of the container was very clean. We applied essentially the same adsorption-desorption competition analysis to try to understand the performance of these containers. In this case, the sample is surface 1 here. The wall of the container is surface 2 here. And we find that due to some mass conservation, we can set up an equation here that's dependent on this surface area of the inner wall of the container. And so that's where this parameter comes into the model. We also have some surface here. It's an imaginary surface that represents leaks. And we look at also, in addition to this, the contamination within just the environment itself. And so we varied the roughness of the surfaces to change this surface area. And then in terms of the modeling, we could look at the hydrocarbon concentration versus time based on the differential equations shown here for the adsorption-desorption competition theory. We could also look at the contact angle versus the hydrocarbon concentration. And this could be maybe assuming a Cassie-Baxter-like model with these defects on the surface, which would look something like this. And then we can combine these together and essentially through our modeling or theoretical analysis, understand the surface contact angle as a function of time for samples that are stored inside of this container. And so again, looking at the container, if we look inside of the inner wall, we had different levels of roughness or surface area. The model predicted the hydrocarbon concentration versus time for the sample, as well as the container wall. The container wall was initially clean. The sample was initially slightly contaminated in the model. And we could also look at things like the contact angle versus time. And these increase, but we find that the higher roughness of the wall results in a much lower level of contact angle and a much lower increase over time of the contact angle, even hundreds of hours later, compared to just the flat storage container. Here are the results. This is the experimental side. So we have some samples here with the three roughnesses of container holding the samples, as well as a sample just stored in lab air. Lab air sample is, of course, the worst. It is an increase in contact angle over a few hours here that then continues to increase over time due to contamination. Sample stored in the clean flat container is better than lab air in blue here, but not much better. Over hundreds of hours will actually approach the lab air level of contamination. And then interestingly, if we start to push to 25 or 50x enhancement in the surface area of this clean container wall, we don't see any increase in contact angle over this period of study here. In this case, the samples are also aluminum, same material as the container itself, and nominally flat. We wanted to see whether or not this approach also would allow us to generate ultra clean, high surface area containers that could maybe be produced in bulk, saved for later, or shipped around the country as a product. And so to probe that question, we roughened the inner walls, plasma treated them for 30 minutes, and then left them empty for 3 or 4 weeks. No sample is inside. And then after 3 or 4 weeks, we started storing samples in these pre-treated containers. A month ago, for example, we treated it and then we just let it sit. Then we put the sample in, and putting the sample in, we have sort of the baseline over here on the left. And we could compare that to, for example, the different types of containers that had been pre-cleaned either 21 or 30 days before storage of the sample. And in all of those cases, both the nano and hierarchical textured container walls far outperformed, first of all, the air at 0 time, and second of all, outperformed what your expectation might have been for having let them sit with nothing in them. So this is sort of showing that you can just fabricate this container, let it sit for a month, then put your sample, and then it still keeps the sample clean for hundreds of hours. We also looked at the performance in terms of taking samples that may initially already be contaminated and using the container to clean them, to remove contaminants, and that worked as well. So in this case, we have the same aluminum wafer or aluminum coated silicon wafer. In this case, we put it in a desiccator for 20 hours with hexane. So we tried to make a well-controlled level of contamination on the surface. That's what gave us this initial contact angle of just over 40 degrees. And then we looked at the evolution over time. In air, it continued to increase. What's interesting is that we see this sort of dip in the flat surface where we had some passive cleaning initially, but then we started to increase in contamination over time. And then the textured surfaces were quite effective at keeping the sample clean over time after initially having some passive cleaning performance. You can look at this in a different way. For example, looking at the effect of the surface roughness on the contact angle at different times. And over time, we find that these higher levels of surface roughness result in a steady or stable level of lower contact angle, even pushing towards hundreds of hours of storage time. And our model, all of the curves in these two left plots are model curves, actually allows us to predict the full design space of what the roughness should be at different levels of time to predict this cleaning performance for samples stored in these types of containers. And so in a nutshell, we basically saw this, first of all, strong relationship, as we mentioned, between the CHF and the hydrocarbon contamination or the concentration on the surface, which represents the importance of trying to understand and control contamination. And to address it, we developed this passive clean storage approach, which is based on basically a sacrificial container. It's a getter for contaminants using the high surface area and initially ultra clean state. And we developed this modeling framework, which first of all predicts the behavior that we observe experimentally quite well. And second of all, allows us to then probe this design space when we want to create future types of storage devices. And we found that this was portable. We could store it before use for maybe a month or more, and relatively cost-friendly or low cost. So this is just aluminum containers that you can buy from Amazon or online. All right. And so now we finally get into the third and last portion of the talk. And so I was talking about the chemical failures. When I was talking about chemical failures, I mentioned a few things that can happen. We focused on maybe the contamination of surfaces over time and how that can impact your experiments. When I talk about thermal failures, I'm going to talk about things that are impacted, in this case, by phase change heat transfer, altering the behavior of the engineered wettability surfaces. And I'm going to specifically focus on super hydrophobic surfaces. And this work is hopefully exciting to some of you in the sense that it's not published yet. It's in preparation now, but you'll be seeing this probably for the first time. I have not given a talk about this work yet, so I'm happy to also hear feedback in terms of what you think in terms of the presentation here. So super hydrophobic surfaces is just some sort of a schematic or illustration of these. We can do things like, for example, self-cleaning with these nice mobile droplets. We can get the jumping droplet condensation that many of us are familiar with. Also can be useful for things like de-icing. Show the plane here with the de-icing fluid, but super hydrophobic surface may be an alternative. And this is a nice video of the potential use of a super hydrophobic coating in this person's attire. This is the ultra ever dry video. I think people remember Never Wet. I always like the two companies. One was Never Wet and the other one was Ever Dry. I'm not really sure what the relationship between those two was. Maybe they were very fierce competitors. But there's a lot of applications for the super hydrophobic surfaces. And in this case, we typically design the super hydrophobic surface on the far right side of this regime map. So in this case, we can use just the chemistry to get up to a contact angle of maybe 125 or 130 degrees. But if we want to push up into the super hydrophobic, greater than 150 degrees water contact angle regime, we would require some kind of a textural roughness. And that's how things like the lotus leaf and also some insects achieve their water repellency, using both the surface chemistry and the roughness of the surface. And so there are a lot of approaches that we can use when we try to make engineered bio-inspired solutions that include things like nanofabrication, maybe also etching of the surfaces. So I showed that for our aluminum ultra clean storage containers, we just use a hot water treatment. That's an effective way to get some nanostructures on the surface. In that case, those nanostructures would be hydrophilic, and we would still need to apply a chemical coating to functionalize or make the structures hydrophobic to achieve super hydrophobicity. And then alternatively, there are some commercial spray coatings that are just off the shelf And so I show here some of the nanofabricated, some of the hot water treated surfaces, and then also the spray coating approach. You can just buy a spray can and spray it onto the surface, and it forms these nice structures, which are also already chemically hydrophobic to achieve superhydrophobicity. But it turns out that there's a temperature dependence of the superhydrophobicity in terms of the impinging fluid. So in this case, we have water droplet. On the left video, the water droplet sheds the surface easily at a very low inclination angle, maybe just a few degrees of inclination in the video on the left, and the drops roll towards us. But if we take the droplet temperature, these are water droplets, and increase it by just 20 degrees Celsius, and watch the video on the right, we get a lot of pinning effect. We get this big droplet growing on the surface that's much harder to roll off. And so this is maybe not the desired behavior. We're requiring maybe much higher shedding angles as the temperature of the impinging water increases. And if we watch this over time, it will potentially even get worse. And the loss of superhydrophobicity when we have hot impinging water is actually already fairly well understood. So we can zoom in at the structure level here, and we have some hot droplet, some room temperature structures. The hot droplet will evaporate. It'll have some net evaporation of liquid water from the bottom surface, and that may recondense inside of the structures. And if the droplet is hot enough, it may be the case that enough of this evaporation and recondensation occurs such that it fully fills in the structures. And so we're no longer sitting on this nice air layer that helps us have droplet mobility, but instead we have this more like a almost Wenzel state. We have this impinged or impaled droplet that's now adhered highly to the surface. And there's a nice work about this. It's from 2017 by the CAREER group, where they looked at a method to overcome this limitation. So they said, we're going to take the surface structures and make them much smaller and closer together. And by doing that, we will be able to have surfaces that repel hot water. And so they say in the plot here on the left that the left column represents a smaller structure. We will have nucleation within fewer of the unit cells. And that means that we will have less adhesion due to these full unit cells filled with liquid. And on the right, they show some traces of droplets during experiments where the smaller pitch, even at elevated temperature differences relative to room temperature, still limits the maximum droplet size compared to the larger pitch in the column on the right. They did this in the clean room. So here are some of the samples that they fabricated, and these push down to the nano scale. So we have some pillars that move down to tens of nanometers in size, fabricated in the clean room. They, of course, also looked at different shapes and found that these nano cones are quite effective. But I think a big takeaway here is that I love the work in the sense that it gives us a very satisfying theoretical explanation and an approach to overcome this hot water problem for the superhydrophobic surface, but it still is fabricated in the clean room. It's a little bit challenging to make these really well-controlled, ordered structures at scale. And so in our case, we're trying to use these spray-on coatings to keep it scalable and make sure that it can be used in real-world applications. But we get this problem on the left, where we get this pinned droplets as the water temperature is elevated compared to room temperature. And we wanted to overcome that. And I'm just going to show on the right our proposed solution. So in this case, we have, again, the 45 degrees Celsius water impinging on a surface. We're calling it a multi-layered insulated superhydrophobic coating. And in this case, we have not just the spray-on superhydrophobic coating, but also a thermally insulating barrier beneath that superhydrophobic coating that helps prevent the evaporation and recondensation from happening by limiting the amount of heat transfer that can occur to the coating. And so this video is showing, hopefully, that it works much better than the one on the left, just the superhydrophobic coating. The idea that I just described is shown schematically here. So we introduced not just the superhydrophobic coating, but also a thermally insulating barrier onto the substrate. And these are both spray-on processes. And the insulation, the insulating layer, has some thermal resistance that we can now tune. We can increase that as we'd like. And we might find in the left column that at low temperature differences, it doesn't really matter. All the performance looks essentially the same because we get very little evaporation and recondensation within the structures. But at higher temperature differences, this can become quite important in the sense that if we don't have any insulating layer, we might fully fill in the structures on the surface and get a high level of adhesion. But if we can prevent the heat transfer and the evaporation and recondensation from occurring, we may significantly limit that added adhesion and maintain the super hydrophobicity. And so again, this fabrication, we've decided to try to keep it quite scalable and simple. So we first spray coat with an insulating open cell foam. And in this case, it's a polyurethane foam. So we have a cross section, we cut it, and we look at the side view, and we just have this nice high void fractions in the foam. Top view shows something that looks essentially flat. So we have lots of pores inside. The top surface remains essentially flat. And then we take this and coat it with a spray-on super hydrophobic coating. And so in this case, we have some SEM images of the coating applied on top of the insulating layer. And together, these give us this mesh-coated substrate. In order to keep things sort of quantitative, you saw the picture here of the layers in between. We have the insulating layer and the super hydrophobic layer. In order to keep things quantitative, we also wanted to compare this to a baseline of a substrate that has been coated with just the spray-on super hydrophobic coating. And so that allows us to have this direct comparison to illustrate the effect of the insulating layer. We want to isolate that, right? And I show here a few images. These are SEM images. We're again trying to make sure we can isolate only the thermal effects and not the textural or chemical effects. And so we look at the textures of the just super hydrophobic coating compared to the texture of the one with the foam beneath. Texture looks almost the same in these two cases, as well as another case where we used some acrylic tape as the insulating layer. Chemistry also is the same because we have the super hydrophobic spray-on coating as the topmost layer. And we did probe the advancing and receding contact angles and found that in all three of these cases, they were essentially the same values. So we keep the texture and the chemistry the same, and we change only the thermal performance using this insulating coating. And so again, here's the video we looked at earlier. We see clearly that the performance is enhanced at these elevated temperatures by introducing the insulating layer. To be more quantitative, we did some sliding and drop experiments. These are inspired by and quite similar to the ones in the prior CAREER paper. We look at the cross-section schematically, and we can see a few different contributions to the force balance analysis. So we have some adhesion force, F in red here, and then we would also have some force that's due to maybe some surface tension effect at the needle. We have some gravitational force, the weight of the droplet, and we also have some force due to the flow coming in and stopping. A lot of these terms are constant. And then we can try to characterize this adhesion force F in terms of two different contributions. One is an intrinsic or innate, just the same adhesion force that you would get on the super hydrophobic surface at room temperature with water. And then one of them is due to this condensation inside the structures, and that can be referred to as delta F that gets added on there. And so those are sort of shown schematically in these two pictures. F naught is just what you'd expect for the super hydrophobic surface at room temperature, and then we might have some evaporation and recondensation inside the structures that gives us a delta F, more adhesion. Now delta F in this case should be equal to, based on the equation up here, a delta mg sine alpha. Alpha is constant, so it should be basically equal to a delta m. And so we can do experiments where we look at the change in the mass of the droplets as they slide off to characterize this change in adhesion force delta F. That's why we do these experiments, and we did them both on the super hydrophobic coating only and also on the mesh surface. So we can look at these, and we basically look at the video one frame before the droplet detachment. And we find that in this case, at room temperature, they look identical. But as we go to higher and higher droplet temperatures, we start to see increase in the departure size for the super hydrophobic coating only to quite large droplets, whereas that is minimized with this mesh surface with the thermally insulating layer. And so it's shown quantitatively here. These are just the changes in the sliding volume that we calculated through image processing versus the droplet temperature. And we can kind of understand that in the context of the model. And we can rearrange that, and we can also think about the limits or bounds of the model. So certainly we can have this delta F if we fill in some fraction of the unit cells such that this S, the fraction that's filled, is less than 1. But we can also imagine filling them all, and this is the maximum adhesion force or the maximum delta F that we can get. And so we should have some plateau with this. And so we can see that that plateau also arises up here in terms of the sliding volume. So we have increase. And not only that, but we've also done this for many different thicknesses of the insulating layer. And we see that as the insulating layer thickness goes down, we have more sliding volume or more adhesion. And so this is due to this evaporation and recondensation mechanism. We did some heat transfer modeling to try to model the process. There's a full network here, but we found that we could make some assumptions and simplify it to the one that's shown on the right-hand side of the slide. And from here, we can combine the two thermal resistances for the superhydrophobic coating and the insulating layer, and basically use this to get the heat transfer. Heat transfer is a function of time in this case, and it also has to be integrated over time to get the total volume of the drop right before it detaches. So we basically apply some analysis here, do all that to get this volume, and this is going to be the volume that we get at the departure. And I'm going to go back to the experimental results here. So these are the sliding volumes at departure. We can convert these over to some delta F, some change in adhesion force. And we can plot this along with the model that I just described. And we get what I would say is a pretty good agreement between the model and the experimental data when we look at this adhesion force. In this case, the delta F is related to this fraction of filled in unit cells on the surface. We can also find that this fraction of filled in unit cells at the surface hits 1 at different temperature differences for different insulation thicknesses. And so we see these cusps, and we can correlate them to temperatures on the x-axis. And if we do that, we can basically define what's called a critical delta T sub C here, where that transition occurs. And it turned out that this was a really convenient way to non-dimensionalize the behavior. We non-dimensionalized our horizontal axis with this delta T critical. We also non-dimensionalized our vertical axis with delta F max, which happens when all the unit cells are full. And non-dimensionalizing this, the data set looks like this compared to sort of the universal model shown in black on the left-hand side. So we're happy with the agreement. There's a little bit of disagreement down here. Some of you may already be sort of thinking about why that is. This is the thickest insulating layer. And so our model right now has the assumption that there would be, as thickness goes to infinity, no heat transfer, and totally neglects the thermal mass of the coating itself, the insulating layer itself. And so that's what we hypothesize as the reason why there's some disagreement as we go to very thick insulating layers. So we did a few other experiments, and we get into some more qualitative stuff here. We did some rebounding of a jet on the surface. This is at 25 degrees Celsius, so room temperature. And it looks maybe as you'd expect, bounces off. Then we went up to 75 degrees Celsius water. And in this case, we compared the superhydrophobic surface only, the spray-on coating only of the superhydrophobic material, to our mesh coating, and found that there was a pretty marked or distinct difference in performance. So we were encouraged by that. We did this over a bunch of different temperatures, as well as insulation thicknesses, found that the results agreed with our expectations. And we also did it over time and found that even as we approach longer times, we don't lose this effect of the maintaining superhydrophobicity with high temperature difference. Did some durability testing. We looked at the robustness in this case by scratching the sample surface or the coating surface with the razor blade. We can visually see some of the marks that form on the surface. And then after that, just looked at the departure size and found that it was not changed, even with hot water. So this is water at 65 degrees Celsius on this marked up or scratched surface. So that was promising in terms of the robustness. Then we have a couple more demos here. So we'll finish out with a few videos that show the performance. Left-hand side is superhydrophobic coating only. Right-hand side is the mesh coating. And we're pouring 86-degree water here on the surface. And the left-hand side is stained by this hot water. Right-hand side is not. We can look at this also in the context of the IR imaging. And so these should be synced up to each other. Quite hot water poured on the surface. And both sides of the surface do get hot, but on the right-hand side, the top layer of the surface gets hot, but it stays hot, does not penetrate through to the bottom. So I'll show a couple more things such that we can wrap up regarding food, and then I'll be done. So we looked at milk. Room temperature milk is shown here. Left-hand side is superhydrophobic only. Right-hand side is the mesh coating. And we skip ahead to the hotter milk. we see the behavior that we expect based on our results previously with water, in the sense that we have some sticking or adhesion of the milk on the left-hand super hydrophobic surface, but on the right-hand side, we basically have a really nice droplet shedding without adhesion. Did the same thing with coffee, and so I can sort of fast forward through us making coffee, and we just pour it on the surface. Super hydrophobic surface fails due to this evaporation recondensation, and the mish surface does not. And then we looked at one more demo here, split pea soup. And so with the split pea soup, we have it in the crock here. It's quite warm. I believe we'll probably have an IR video there as well. And we pour it into the two bowls coated with left-hand side super hydrophobic, right-hand side mish. And we pour it out. Left-hand side of the bowl is totally coated and has like some stuck food. Right-hand side, we have a few droplets stuck, but the performance is clearly much better in terms of repelling the food product. So we can conclude by saying we developed this coating using the thermally insulating layer that repels hot water droplets. It's scalable. We predict that it's about 4 orders of magnitude cheaper than fabricating a surface in the clean room. We looked at modeling the performance, comparing it to experiments, and also non-dimensionalizing it. We were encouraged by that result. Then we also did a bunch of demonstrations to show how we might use this kind of spray-on mish coating in our ongoing work. Just touching on the two things earlier, we looked at contamination in ultra-high vacuum, and we also looked at mitigating it using ultra-high surface area clean storage containers. And the last thing I want to say is that all the work that I've highlighted today has been led by PhD student Jen Liu. I think she's on the call today and also is on the job market. So if people have open academic positions and find this work interesting, please get in touch with me or with her. She may also be considering some postdoctoral positions. All right, thanks.
Thank you very much, Dan. And now the floor is open for questions.
Can I ask a question?
Hi, Patty.
Hey. So I think it's interesting with this higher temperature and especially that you use IR imaging. So when we did experiments with droplet impact on hot surfaces, so we heated the surface, not the water, after a certain amount of time, we also saw a degradation. And that happened with surfaces that were on the order of 60 to 80 degrees Celsius. So I was wondering whether, so I saw in one of your slides, you went up to 600 seconds, so 10 minutes. Whether you do see over time, because if you have the insulation, you should over time accumulate more heat, right, on your sample. So technically your sample should get hotter than on a super hydrophobic surface without your insulating layer. So I wonder how steady state compatible this surface actually is.
This is a good question, maybe from even two different points of view. One of them is that we are definitely lessening the amount of heat transfer that occurs, but still some occurs, and we may still have evaporation and recondensation in the structures at a much slower rate, but one that is not insignificant over maybe hours or days, such that it still fills in the structures. And second of all, because like you said, this will actually maintain the surface at maybe even a higher temperature than if we had just the super hydrophobic coating, such that we could have maybe a thermochemical degradation of the coating, not just this evaporation recondensation mechanism. And so that's something that we're probing now. I think we've gone to a little more than a week in stuff that I didn't show today. And it still continues to work for maybe a delta T of plus 60 Celsius, so something like 80, 85. But I'm interested in exploring it a little bit more quantitatively, which we haven't done yet.
Cool, thank you.
Matteo and then Marco.
Yeah, first of all, Dan, thank you very much for this beautiful talk. I really didn't see the time passing. And I actually have a question that was triggered by your studies, I believe with young soap on the silicon contamination. Now, if I understand correctly, those results were with water.
Yes.
Okay, so the question I have is, if you use dielectric fluids such as Novec fluids or similar products, those fluids are known to be highly wetting, and someone also call them cleaning fluids. So I wonder whether you guys had the chance to look into the effect of contamination for that class of fluids?
I do not recall having looked at this as part of that collaborative work. And I would guess that it does a great job of eliminating the source of error. So as you mentioned, they're very highly wetting. Even if we have some contamination on the surface, probably our contact angle is still essentially 0 degrees. I don't imagine that we have any difference in the thermal resistance due to some thin contamination layer. So I would guess that for the boiling performance, it should probably be essentially the same, whether it's contaminated or not. So
Okay,
that's
your hypothesis. But
hypothesis. Have not tested.
Yeah. Okay. Thank you very much. Then.
Yeah.
Beautiful work.
Marco, please.
Yeah, I think it was very interesting, and I echo Matteo saying that you had delivered really very interesting presentation. 2 questions. One, in fact, is not a question; is something that also Patty said. I'm expecting that if the problem is the condensation, in order to have a transition between the Cassi and Benz state, right? And this is something that was already explored by Patrick and by CAREER and others. The point is that with the thermal layer is really interesting. However, also for me, I'm expecting that at the end, you're going to have a temperature that is enough to prevent the condensation. So this means that, for example, you may have back, let's say, a superhydrophobic surface if you are waiting a little bit. So I was wondering if you did experiments, let's say, with over a long time of impact between the droplets or jets and the surfaces. So this is the first question. Do you want the second one, or?
Let me think about this one first. So I think that if we do the long-term experiment of just the repeated impingement, eventually we may have some failure. We've already gone to a week right now, but only about a week. But if we do the wetting of the surface and the surface does fail, and then we wait maybe a day, it will evaporate, and then it should work again. So even for the plain superhydrophobic coating, it may fail at the moment, but then it will
but Daniel, I was thinking to something much faster, in the sense that when the thermal, I mean, you have a, let's say, do you have a adiabatic surface below? I don't think. So the surfaces I saw are in air. So this means that, in fact, you have a small heat flux on the surface. So this means that at the end, if you have water at 75 degrees, also the thermal layer, let's say the isolation, can reach a higher temperature, and then you're not going to have condensation anymore. So understand what I mean?
Oh,
it's not a question of weeks, it's a question of minutes, or let's say hours. I don't know.
Yeah, so this is something we noticed from some of the IR imaging, is that the surface gets hot much faster when we have the insulation layer and remains hot. I think that it is not able to fully prevent the evaporation recondensation, but it can make it much smaller, orders of magnitude smaller rate.
Because I'm thinking that there is a, let's say, this is a mechanism, the condensation at the basis, but there is also a dynamic mechanism linked to the process of the rebounding and so on. So both phenomena, because, you know, a super hydrophobic surface can be statically super hydrophobically, but not dynamically hydrophobically. The sense that when you have drop impact, because of the impalement, the surface cannot be maybe super hydrophobic anymore.
Right.
So so I think that is your idea is really very interesting. The explanation, I think that maybe we should also take into consideration some dynamical effect, not only the possible condensation at the base of the structures.
I would be interested to discuss this more and probably follow up with some area that we could potentially even work together. I think that, yeah, this is our first push to get this idea out.
Oh, but the idea is really interesting.
Hopefully lots of follow-up work.
And the other thing is about the boiling. As you know, we just published a paper in National Communication about the nanoscale origins of boiling. And theoretically, we saw that really is enough a very small variation of wettability in one spot at nanoscale to change completely the situation. So, so that the contamination really can be interesting. In the case of the experiments with the CHF, with the silicon vapor and so on, there are 2 points to say. One thing is that we already saw that even a nano cavity, the cavity of the order of 2-3 nanometers can change the situation, first thing. And the second one, consider also that it's not only contamination. For example, the problem of the dissolved gas inside the fluids, the presence of nanobubbles on the surface, this can change again the surface conditions. And in many experiments, I mean, it's not because they are not good, but because it's very difficult to control the situation.
Yes.
It's really difficult to have the same conditions, really, because the conditions are not at the micro scales, but at the nanoscales, where it's very difficult to control them.
Let me then moderate the claim here to say that we identify one source of the error in the boiling experiment that you could control among many.
Exactly, I agree. Yeah.
Okay, I think we're already running late. So with that, let's thank Dan again, and goodbye, everyone, I guess.